A very interesting set of experiments emerged from studies in Pavlovian conditioning that called into question many presumptions in learning. And we now refer to these affairs or these events as the biological constraints on learning. Early on in the study of learning, there were many theorists and people supposed that there could be, or we could discover, general principles of learning. What that meant was, are there features of situations in learning experiments that apply to everybody and to everything? General. They apply all over the place. Or are the results of learning experiments and the conditions and situations under which they proceed, are those dependent on an animal's genetic makeup? So the general principles of learning, or the premises, were that these were based on three, in which we talked about the general principles of learning: contiguity, frequency, and equipotentiality. Now, contiguity refers to things appearing together closely in space and time. Frequency is more frequent the better. And equipotentiality was that all stimuli are equally conditionable in the Pavlovian conditioning world. I'm going to talk briefly about an experiment in which contiguity and equipotentiality are sort of called into question. So, general process learning theorists hypothesized that for effective conditioning, the CS and the US must be close in space and time. And this turns out not to be true. This turns out to be absolutely false. Garcia and colleagues in 1969 did the following experiment. They presented a CS, and then after some delay, they presented a US. And the US in this case was lithium chloride, which is a drug that makes you sick. And they did this with rats. In rats, what they did was they presented sweet water. So they presented sugar water, or saccharin water, and then 22 minutes later they induced sickness with lithium chloride. And this produces vomiting and gut wrenching and gasping and gagging and so on and so forth. And then the next day, they presented the sweet water, and the rats avoided it. Sometimes later, Etzkorn and Stevens found that even a 24-hour delay was effective in this kind of presentation. So this illustrates, and this has become its own field really, that we now refer to as taste aversion learning. And I think it's a special case of, or broadly under the case of Pavlovian conditioning. It really destroys the contiguity principle, and that is to say that the CS and the US don't have to be close in space and time. They can be delays of up to 24 hours and them still be effective. It turns out that this is somewhat useful. We find that in chemotherapy situations, people often, before starting chemotherapy, will eat a favorite meal. And then they go and get this intense drug and radiation therapy and so on. And it makes them sick, and they vomited it all up. And after their treatment is done, we find that they never want to eat that meal again. They never want to eat that food again. We find this often in kids and things like, a McDonald's Happy Meal. They have a McDonald's Happy Meal and then undergo chemotherapy, get sick, and then never want McDonald's again. Maybe that's a good thing, but generally think it's a bad thing. This, we think, is a result of taste aversion learning. You probably may even have friends, or maybe you've even experienced this, where you ate something and then got sick shortly thereafter, and now you don't have a taste for it. This illustrates taste aversion learning. It also absolutely destroys the contiguity principle as a general process learning principle. We also use this. There's a video that I put up online that shows how sheep can be conditioned to avoid certain crops. We also have tried to use it with wolves in the West, avoiding sheep and other herd animals that farmers are using and raising. In the West, where there are large expanses of grazing area, what we have is we've had a problem with predation, or natural predators coming in and eating calves or eating sheep, and this is costly to farmers. One way to get rid of that is to go shoot the wolves, but that's probably not the best practice either. But what we've done is we've poisoned um, carcasses, for example. The wolves will eat the carcass, get sick, and then never want a sheep again. So we sort of scare them off, if you will. So this has been a really, really useful principle. It is such a powerful principle and such a powerful procedure that we use it to test the effects of all sorts of things. So maybe, I have a friend who we were drinking one night, and he ate a whole bag of nacho cheese Doritos, and then got really, really sick from drinking, and never wanted another nacho cheese Dorito. Couldn't even stand the smell of them. So that illustrates, I think, taste aversion learning. We know a lot about taste aversion learning. It's really interesting. Like, for example, pregnant women are more sensitive to taste aversions than when they're not pregnant, which is really interesting because they want to probably avoid bad stuff if they're carrying a baby. So it turns out that taste aversion learning highlighted what we call biological constraints on learning, and that is there are limits to what we can do, what animals can do, what humans can do. And then there's also sensitivities to certain things. We come preloaded with certain behavior patterns. Some species are more sensitive to certain events than other species, and not everything can be taught to every organism. There's a famous saying by Robert Heinlein, which is never teach a pig to sing, it wastes your time and annoys the pig. There are constraints, and we recognize constraints in learning. And in conditioning with certain things, with certain stimuli, we see certain effects that we don't see in others. So we know that there are biological constraints, biological restrictions on what animals can do.